Hello, JSConf. Before I begin, I just want to thank all of you for giving me this opportunity. Around 10 years ago, I left my hometown in the heart of the northwest of Argentina, and I literally could not have envisioned that I'll be here speaking today to all of you. So thank you. Earlier this week, actually, I was asking all the speakers online if they had any rituals that they took before going on stage. This is the largest audience I've been in front of. And Lori Voss suggested I take a selfie to help me with my stage fright. So if that's OK with you, could we take one at least? Yeah? All right, let's do that. Thank you so much. So we go there. Can we say actors? We'll see why later. 1, 2, 3, actors. Nobody? OK, well, it was worth a shot. So, all right, for those of you who don't know me, my name is Leandro. And I work as a research engineer at Source, the Stockholm Research Center. We're a fully open-source nonprofit dedicated to advance humanity and our interactions with computers. Today, I'm here to talk about us, all of us, and about our history building software for human beings. Hopefully, by the end of this talk, I would have done 2 things. The first one is I would have shown you that while the web today flourishes with incredible ideas, we have a great many lessons to learn from our past. And the second one is perhaps I will have compelled some of you to challenge the ways that we build web applications, both at a technical level, but also philosophically. So let us begin. And in the spirit of fun, let's play a small game, right? I will describe a program and some of the features it has, and you'll try to guess out loud its name. Are you up for it? Yeah, cool. I know we're all tired this last day, but please bear with me. Can you think of a program that lets you draw, maybe free-handedly, right? And then you can resize your shapes at will? Does this program let you set constraints for those shapes and say that they will be centered or maybe parallel to something else or evenly spaced? Can you make copies of those shapes? And if you make a copy and update the original, does the copy update as well? Anybody, any guesses? Photoshop? Anyone else? All right, I was hoping someone would actually say Sketch. These are some of the features that you can see in Sketch. But in reality, I was referring to Sketchpad. Sketchpad is a program developed by Dr. Ivan Sutherland back in 1963. And yet, this is this old. This is really over 50 years old. So I want to show you a little bit of what Sketchpad looks like. Let's play that. We can see that he just starts sketching something on screen, right? It looks like a rivet or maybe some sort of like square with a base. He has a crossbar, and he's using the center of the crossbar now to draw an arc, right? Then he's going to point to the different edges of the drawing, and it's going to ask the program to make all of them mutually perpendicular. Turns on the constraint solver, and as the program solves the constraints, it forces the crossbar to change, which forces the arc to change, yielding this perfectly symmetrical rivet. This is really old stuff. Then he shows that no matter how you distort it, it comes up with a symmetrical solution, which is pretty cool. These constraints could have been more complicated, right? Could have been ratios between lines and, or to other drawings. We'll see one last example there. Turns it on. There you go. Perfectly symmetrical rivet. Another important idea that we'll see here, and it's practically the first time this was shown, is the idea of a master and an instance, right? He was working before on this master drawing, and now he has an instance of it on screen that is completely independent from the master. You can see that he's rotating it, he's trying to fit it into the plank. It's a tedious process. It takes a little bit of time. The display flickers because it's not actually a display, it's an oscilloscope. They did not have displays back then. And perfect. There you go. Took me a long time to time that. But we can relate nowadays to this pattern using different names. Perhaps we think of components and elements in React or classes and objects in JavaScript. He creates a few more instances, then he goes back to the master, and you can see that he'll just remove some of the crossbar lines. And when he goes back, lo and behold, the copies, the instances, the elements have been updated. This is the work of Ivan Sutherland, who in 1963 published his seminal work called Sketchpad. The thesis is online. You can read it. It's pretty intense. Ivan Sutherland did this development during the thesis, right, all by himself. And when Alan Kay, one of his students, asked him how did he manage to create this first object-oriented system and the first graphical interface system all within 1 year by himself, the guy just replied, well, he didn't know it was hard, which is interesting. Either way, Ivan really set the bar high for the people that came after him, right? He set a direction for the likes of Douglas Engelbart, for example, the fellow who created the first computer mouse. And Engelbart and his team at the Stanford Research Institute, they developed during the span of around 10 years a system that is kind of incredible. I can't quite grasp that it has existed. The system was called the online system for historical reasons that I'm not going to get into. And it was first demoed publicly in 1968. So what I'm going to show you right now dates a long time ago as well. This has been dubbed the mother of all demos. Let's look at why. And this is audio, so hopefully it will be not too loud.
The display we have. I'd like to see you while I'm working on it. So,
oops.
Available to the kind of display we have. I'd like to see you while I'm working on it. So, before I can do that, I'd have to set up my display in a certain way.
We can hear here Douglas doing a live stream of his computer.
So I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine.
And it's going to fit in a video stream from a different computer from somewhere else in California.
Audio, you can see my work, you can point at it, and I can see your face, and we can talk. So let's do some collaborating.
That's video conferencing. 1968.
What do you want me to say?
Yeah. There's nobody here but a large audience, Bill.
All right.
All right. So let's go talk about information retrieval. And there are a lot of things I've been showing them and jumping around and finding your way.
Can we lower the volume on the video, please?
To the portrayal I gave about NLS as an instrument on complex data structures. It shows them how we can get around and find things. I showed them the content analyzers.
They're discussing some matters of the presentation they were doing there, and then they proceed to link workspaces to the point that they're essentially doing live coding. If you look carefully, in a second from now, you're going to see two mouses on the same computer. They're actually modifying the same environment. This is live coding. I mean, seriously, this presentation is epical. If you haven't watched it, after this talk or whenever you're home, just look it up on YouTube, the mother of all demos. There you go. You see two mouses there. It's kind of insane. But yes, with this contextual background, we can move on to the last piece of history that we need for this presentation. And that is Xerox PARC, the Palo Alto Research Center. In this branch of Xerox, we found the likes of Alan Kay, Adele Goldberg, and Dan Ingalls, who created Smalltalk. Smalltalk is a language that was designed to be a vehicle for human-computer symbiosis. And I'm not talking about symbiosis like the Borg in Star Trek. It's a language that is designed to fade into the background fast and let you express yourself, sort of like a musical instrument would. It offers the programmers two core capabilities. The first one is classes and objects, which are used to represent things, right, and processes. And the second one is message passing. That provides a communication layer, right, a way for these objects to talk to each other. Something worth noting is that Alan Kay has repeatedly said that when he invented object-oriented programming, the important part was not the objects themselves, but the messages. It was the communication what he really cared about. Let's look at an example of this system. We can see here an animation of a ball in what appears to be some sort of a static website, right? But in reality, the animation is being programmed as objects. So we can stop it and step through it. So you can see here, it's going to go through it until it finds the right frame. He then opens up a browser, and this browser lets you see the messages that this object in particular can receive, right? That you can send to it. After finding the right message, he's going to go into the painter tool and do the same thing and find that, OK, we have the current frame message on the top, and we need to find a message to link the current frame into the painting tool. So it's going to look for the picture arrow. It's It's going to then sort of sketch an arrow, and the system will recognize that you have two messages selected. You want to send a message from between objects, so you can type in there what is it that you want to say. So he's telling, hey, painter, here's a message picture. Give me the picture that you're currently using. I'll link it to the bouncing, which is the name of the object that represents the animation, current frame. So the current frame of the animation above. And after he sends the message, boom, we get the frame below. This is done completely live. This is not something that has been prepared beforehand. It's the live system that the user is actually going to use, right? All of this can be built. All of these applications, right, are customizables by the users to feed their needs. They really turn the whole computer into some sort of bicycle for the mind. And all of these examples have been built on each other to formalize the idea that our world is concurrent. Everything around us is happening in parallel from us. We communicate with everything around us by sending these messages. Just like right now, I'm not letting you access the memory in my head. I'm sending messages to you so we communicate. Yeah. The underlying philosophical grounds that all of these people shared, the vision they had, was to advance the human intellect. We're not talking about for-profit companies trying to lure you into buying a product, but about altruistic men and women dedicating their lives to forward all of us. So we've seen the Sketchpad, the NLS, and Smalltalk. Now, what are some of the learnings we can take from them and apply today? I want to talk about two things, two ideas. The first one is the computation model behind these applications. How is it that they run? And the second one is the philosophy behind them. So let's begin with the first one. When we model an application in Smalltalk, we model it in terms of objects that interact with each other via message passing. Each one of these objects performs, hopefully, one very small task. And that's a number of messages, right, that it understands and that it sends to other objects. It may have some internal state that can change over time. Normally, one of these Smalltalk applications, right, can have millions or hundreds of millions of objects, and you may even think of those tiny objects as tiny computers on their own. It's kind of like an internet inside of your application. If we look at this diagram, we can see that we have some button that's sending essentially an input object, a message called clear, so it clears itself. And a container object is sending a draw message to tell the input where it has to be drawn. The same happens with a slider that is linked to a graph, so you can update the graph through the slider. And the synchronizer might send new values into the graph that will, in turn, update the slider. The underlying principles behind how Smalltalk works, right, have been formalized with some differences as the actor model. In the actor model, we have separate actors, essentially independent entities, right, that they're executed completely independently, completely in isolation. They solve problems by collaboration, and they collaborate with each other by message passing. They collaborate by talking to each other, just like humans do. Modeling the system with this approach has three interesting properties. The first one is failure isolation by default. The second one is an asynchronous nature, and the third one is that it's trivially parallelizable. Let's talk a little bit about the first one, then we're going to go to the second and the third. Show of hands, have you ever seen an application, a website, that was completely unusable because of some unhandled exception that blew up the complete application stack? Yes or no? Pretty much everyone in the audience is like, yeah, that's the way it goes. I think we all have, right? If our applications are normally composed of dozens of these independently collaborating systems, why do we treat them as a single monolith that has to be very, very carefully programmed? I don't quite understand that. We know that our applications are scaling massively in complexity, right? And preserving these user experiences for the people that use them is perhaps the definition of a day job for some of us. So why are we risking so much? In the actor model, an actor failing does not take down the entire system. In fact, if you build it carefully, other actors can take a look at your actors, right, and restart them whenever they fail. So you have a system that heals. Of course, we could decide that certain failures are worth a complete application crash, irrecoverable crash, but now it's a conscious decision that we make. It's not something that just happens. The second thing I want to talk about is the synchronous nature. And this is fairly straightforward. The applications that we build are asynchronous by default. The user interacts with it, and we don't know when that's going to happen. So why do we need to build up stacks of reactive libraries to be able to act through in that way, where we could be using a computation model that's fit for it? And lastly, trivially parallelizable. We struggle to parallelize these single stack based applications because we have a single stack running in a single thread, and any coordination between threads has to be thought beforehand and has to be done manually. But when we're thinking in terms of actors, we could potentially run every actor parallelly. That might be useless because some of them might depend on messages from each other, but you can do that. This is because each one of these actors is essentially its own tiny computer. Just think of the performance gains some applications would have by just using more cores because they are available, without having to be rewritten. There's these three properties, right? They are incredible in practice, most notably in platforms like Erlang or Pony, when they are normally used for building massively concurrent systems. Systems like WhatsApp, for example, were built on it. I will grant you that we probably don't want 2 million users per browser, but knowing that your application can crash and recover on the fly by itself is incredibly powerful when it comes to raising the bar on quality of any experience that we design and develop. The second point I wanted to make, beyond the computation model, is the one of philosophy. And this is a briefer one. It's the last point I'd like to make today, and is that most Smalltalk applications, if not all of them, are built on two key ideas. The idea of liveness of an application and the idea of directness of an application. When we talk about liveness, we're talking of the ability to always respond to a user's actions. This means that whatever you do in the system and whatever the system is doing, there will never be a complete stop, a complete gap in the feedback loop. This is a little bit how the real world works. We're constantly sending messages. Sometimes we get responses back. Sometimes we get, double tick red. But naturally, as the workload of the system increases, you will expect some performance degradation. You would expect the system to gracefully degrade without actually stopping to work entirely. Now, do you remember the last time you were on a website that just didn't do something or anything really for some time? There was perhaps something taking over the main loop, and your application just sort of stopped working entirely. Really, we can do much better than that. And I think considering liveness and the actual model, how they work together, this failure isolation is foundational to recoverable errors. The second thing in the philosophy track is directness or directness. Directness means that everything you see can be modified. Whatever the user is seeing on screen that he can click or she can click on, whatever graphical representation of the system we have, is a point at which the user can begin to explore the entire system. That might be scary for some because you can right-click on something and get access to the actual source, not some bundled and minified version of it, and modify it. But if they can inspect the button, right, if you can change the attributes, restructure the behavior, even reconstruct a user flow to suit their needs better, persist those changes and essentially modify everything that they already see, we have an application that showcases directness. Really, this is a deeper philosophical question to ask to all of you here is, are we going to be building applications that model a flow that everybody sort of understands and doesn't actually empower anybody to do better than they actually are doing? Are we going to be giving them bicycles for their minds, for their processes? Or are we just going to carry them around hand in hand? So how do we get there? I mean, I would venture that most of you haven't heard of me before, so it is likely hard to agree with me right now that we need to rethink the complete foundations on which we build applications. After all, with all these fancy frameworks out there, backed by huge corporations, how could they be wrong, right? So I just invite you to take a first step into this world by trying out Faro Smalltalk. Just to get a feeling of what we're missing in web development nowadays. What is it like to build user interfaces, user applications, user experiences in other platforms? Faro is a dialect of Smalltalk that is quite alive and has a growing community in France. It's mainly developed at INRIA, I believe. And it should be more than enough to showcase why some of these attributes are paramount to increasing the quality of the software that we build. you'll find that the same properties alongside a highly reflective language allow for a development experience quite unlike we have seen in other mainstream languages. But seriously, oops, sorry. But most importantly, what is it that we can do right now to start building web apps like it's 1972? And my best answer to all of you is to start by learning about them. Look online for videos, people that put screencasts on how to build these applications with these technologies. There's tons of languages out there from then and newer, like Smalltalk, Self, Modula, Logo, Faro, Squeak, just random names. I feel like I'm reading a lot of NPM packages right now. And really just try to get inspired by the mindset. Take a look at how they're thinking. What is it that they want to give the users? Are they trying to just solve the problem? Are they trying to give them a tool? Start by asking, why are we treating people, this is kind of strong, but as cattle to put through a conversion funnel instead of empowering them to solve their problems by giving them flexible systems with powerful tools to be as efficient, as effective, and effective at their jobs as they can be. I'm sure that we all are aware there are learning curves for these things, but if humans have proved capable of anything, is of growing and learning, so there's no good reason to stop doing what we're doing. To not stop doing what we're doing and reconsider it. We can begin today with just a fundamental philosophical shift. In the meantime, at Source, we're working as hard as we can on formalizing and implementing a universal actor virtual machine. We're calling it Stage VM. We think it's a pretty good pun. That we can use to bring this computation model and some of the goodies that we see in all these languages to the browser via WebAssembly. The idea is not just to target the browser, but to do it through WebAssembly. It will be some time before we have something worth demoing, but if you're interested, don't stop following source_technology on Twitter. And with that, I want to say, if you're interested in nonprofits for software, I work at one. If you're interested in the actor model or want to learn more about Smalltalk or Erlang, distributed systems, or concurrency, please come and say hi to me after this talk. We can chat. Thanks a million for the opportunity, and enjoy the rest of JSConf.